Hey folks, welcome to another set of Chemistry 1 video notes. Today, in our second lesson of Unit 6, you'll be learning about the types of chemical reactions and how to predict the products of them. This lesson covers standards C.4.1 and C.4.2, which ask you to describe, classify, and give examples of various kinds of reactions and to be able to predict the products of those types of reactions. So, let's get started. Our first reaction type is called a synthesis or combination reaction. This is when you take two substances, either two compounds, two elements, or a compound and an element, and bring them together to form one compound. The important thing to remember here is that we start with two substances in our reactants, and we end up with one substance in our products. The example we have here is the combination of three magnesium atoms with one molecule of nitrogen gas. They come together to form magnesium nitrate. You can remember this one as thinking of synthesis as combining things together. Our next type of reaction is a decomposition reaction. This is basically the opposite of a synthesis reaction. In decomposition, we start with one compound in our reactants, and then it splits up into two smaller compounds, two separate elements, or an element and a compound. Our example here is the decomposition of hydrogen peroxide. The hydrogen peroxide breaks down into water and oxygen gas. You can remember this one by thinking of decomposition like decomposing food, as being the process of breaking something down. Our third type of reaction is called single displacement. This is when we displace a single element from a compound, and then we switch it with another element. So we start off with a single element and a compound on the reactant side. Then in the product side, we form a different element and a different compound. Our example here is a reaction that takes place between zinc and hydrogen sulfide. The zinc switches spots with the hydrogen, producing elemental hydrogen and a compound called zinc sulfide. Double displacement is very similar to single displacement, except this time we're displacing two elements from two compounds. So we start with two compounds in the reactants, and they perform a switcheroo, giving us two different compounds in the products. Our example here is the reaction between magnesium oxide and calcium sulfide. Notice in the products, the sulfur and oxygen switched, giving us magnesium sulfide and calcium oxide. There are three important types of displacement reactions: precipitation, gas formation, and acid-base reactions. In a precipitation reaction, you form a new compound that's an insoluble solid. In other words, one of your products will not dissolve in water. If you're given the reactants of a double displacement reaction and you find that one of the products is an insoluble compound, that reaction is most likely to take place. If both of the products are able to dissolve in water, then no reaction takes place. Gas formation reactions are very similar, except instead of forming an insoluble solid, you form an insoluble gas. Same rule goes for this one. If both of the products are gases that are soluble, the reaction doesn't occur. Finally, we have my personal favorite, the acid-base reactions. This is when an acid reacts with a base and forms an ionic compound, which we usually call a salt, and water. In these reactions, acid will give away a hydrogen ion, and the bases will take in that hydrogen ion. And finally, our last type of reaction is the combustion reaction. Any reaction that has oxygen, O2, as a reactant, and it rapidly produces heat and flame, is called a combustion reaction. Most combustion reactions that occur are ones that involve the combustion of hydrocarbons. Remember, a hydrocarbon is a molecule that contains hydrogen and carbon. So when a hydrocarbon reacts with oxygen and fully combusts, it'll form carbon dioxide and water. So why did we just learn all of this? Well, because you're going to be expected to determine the products of a reaction if you know what type of reaction it is. So here are some important things you need to know. When predicting the products, you have to know the charges of your ions and how ionic compounds form. That is extremely important in coming up with the correct products. If you don't remember that stuff, you might need to review your notes or the Quizlet to try to refresh your memory. If one of your products happens to be what we call a Brinkelhoff element, it'll form a diatomic molecule. That means, unlike most elements that are by themselves and form just single atoms, these 7 elements will form molecules that consist of 2 atoms each. These elements are bromine, iodine, chlorine, hydrogen, oxygen, and fluorine. If you can remember the word Brinkelhoff and how to spell that, you can remember those 7 elements because the symbols of those elements are how you spell that word. In some of our examples today, you may have seen some state symbols. We didn't just come up with those state symbols willy-nilly. There are certain rules we use to come up with them. So if our reaction is taking place in solutions of water, we need to know whether our substances will dissolve in the water or not. If they dissolve, we call them soluble. If the substance meets one of the following 4 conditions, it's going to be soluble. If it contains an alkali metal ion, lithium, sodium, potassium, any of those alkali metals, or the ammonium ion, which is NH4+, it's going to be soluble no matter what. Also, if it contains the nitrate, bicarbonate, acetate, or chlorate ion, it's going to be soluble no matter what. If it contains a halogen ion, which we call a halide, it's going to be soluble unless that halide is fluorine, or if it's a halide formed with silver, mercury, or lead too. All sulfates are soluble unless they're combined with silver, mercury, lead 2, or calcium, strontium, or barium. If you're checking your compound and it's not listed in one of those 4 rules I just said, it might be included in the next 2 rules I'm about to give you. These 2 rules cover things that are not soluble or insoluble. If the substance meets one of these 2 criteria, it's definitely insoluble. So any carbonate, phosphate, chromate, or sulfide is insoluble unless it has an alkali metal ion or the ammonium ion. And any hydroxides are insoluble unless they contain the alkali metal ion, an ammonium ion, or barium or aluminum. If you've checked your compound against all 6 of these rules and couldn't find it anywhere, either you need to read the list again, or I might have accidentally given you a compound that isn't on this list. If you have troubles with this one, just ask me and I'll help you through it. So now that we know whether something is soluble or not, we can assign state symbols. You got to check your solubility rules that we just talked about, and if the substance is soluble, we call it aqueous with the state symbol AQ next to it. If it's insoluble, it's a solid. If it's a single element that isn't a Brinkelhoff element, it's usually a solid. If it is a Brinkelhoff element, it's usually a gas. The exception to that could actually be found in the periodic table. At room temperature, bromine exists as a liquid, and iodine exists as a solid, but the other 5 Brinkelhoff elements are all gases at room temperature. Just because something is dissolved in a liquid, that doesn't mean it is a liquid. So if it's dissolved in water, we call it aqueous, not liquid. Water, on the other hand, since it is a substance that is melted, we would call it liquid. Any other state symbols will have to be assigned based on observations you made about the experiment or from clues from the word problems you're given. Once we get the hang of predicting products and identifying types of reactions, we'll get to practice writing out the equations in their 3 different forms. The molecular equation represents the substances as if they exist as molecules when they're in water. Even if they're aqueous and dissolve in water, we just represent them as their molecules. This is the kind of equation we've seen so far. Our example is aqueous lead-2 nitrate and aqueous potassium chromate participating in a double displacement reaction, forming solid lead-2 chromate and aqueous potassium nitrate. In a complete ionic equation, we write out that whole equation with all of the aqueous molecules split up into their different ions. This represents them as being dissolved in water like they actually are, and it's a much more accurate way to describe what's happening. In order to do this, you have to know the charges of different ions and how ionic compounds form. So again, please review that if you've struggled with it the first time. Notice our solid lead-2 chromate did not get split up into different ions. That's because it's not soluble. It doesn't dissolve in water. Finally, to get the net ionic equation, we cross out the ions that aren't participating in the reaction. We call those ions spectator ions because they're just sitting there. They're the same in the reactants as they are on the product side. This leaves us with only the precipitate in the products and the ions that form that precipitate in the reactants. Well, that's it for today, folks. I hope this video helps you recognize the different types of reactions and be able to predict their products given enough information. As always, if you have any questions, please ask.